Okay, you can still see that as delta x goes to 0, using Taylor series analysis, you're going to see this term is small. It's on the order of delta x. This term is on the order of delta x, right? Because cosine of k delta x deviates from 1 with a magnitude of O delta x squared. So this whole thing is O delta x. And this whole thing is ik, right? If you let delta x goes to very small. So we still have the good approximation of the behavior of an analytical derivative when delta x is small. But this term is actually going to contribute to the stability of the discretized equation. And let's actually start to look at how does it contribute. So if instead of we have the exact differential equation, what if we have du dt plus a times this finite difference equal to the second derivative? Then if we plug in all these Fourier series and match the coefficient, and now this contributes to the coefficient, right? It's no longer the ik. What we get is a du head of k dt plus a times this thing, times this whole thing with real and complex components. Times u head of k, right? I mean, this also comes into the coefficients of these Fourier modes, is equal to kappa, I mean, there is a minus sign, kappa times k squared. I mean, assuming we didn't discretize the second order term. I mean, if we discretize the second derivative term and do a corresponding Fourier stability analysis, we should be able to figure out what that comes to be. But let's just keep that analytical for a moment. And you can see that this term, the real component, now actually affects the stability, right? And the way it affects stability actually depends on the sign of this a, the wave speed here. If the wave speed, first of all, let's actually figure out what's the sign of this thing. Is this greater than 0 or less than 0? Yeah, what's the sign of this?
Less than 0?
It's less than 0 because cosine is always, less than 0, right? So the stability of this thing actually, when it depends on when you pull this thing to the right hand side. And if a is greater than 0, right? If a is greater than 0 and a is multiplied by something less than 0, so the whole thing is less than 0 when it is on the left hand side, which means when you move it to the right hand side, it will be greater than 0. A greater than 0 real part on the right hand side of an ODE contribute to instability, right? It is going to contribute to instability. And that is why you don't want to use this kind of right biased derivative, right biased finite difference, or for that matter, a right biased finite volume or even finite element when you are discretizing a linear advection equation with a wave speed of positive. A positive wave speed, that means the wind is blowing from the left to right? And if you use a right biased derivative, it's a downwinding scheme. And the downwinding scheme contributes to instability, as we have seen, I think, twice in our previous lectures. But if a is less than 0 and less than 0, it has a positive sign when it is on the left-hand side of the equation. And when you move it to the right-hand side of the equation, it's a negative sign times u hat of k. So if a is less than 0, the artificial real component of this finite difference scheme contribute to stability, right? So that's why you actually want to use some upwinding. This is when A is less than 0, the wave is moving from right to the left, and looking towards the right is actually looking towards the upwind direction, right? So it's upwinding. A similar analysis can be done with a left biased scheme, and you reach exactly the opposite conclusion. If A is greater than 0, a left biased scheme contributes to stability, and when A is less than 0, a left biased scheme contributes to instability. So this is an example, really a first example of how useful Fourier stability analysis can give you, right? So for different schemes, this converts not only the analytical derivatives, but also the numerical derivatives into really decoupled ordinary differential equations. It's decoupled for different wave number case. For every k, you get a different ODE, and you can analyze the stability and instability. In this case, we concluded that for any k, right, the contribution to stability is the same when we apply an upwinding or downwinding scheme. It just depends on the sign of A. And in reality, if you look at a different scheme, as long as some of the case are going to be unstable, you get an unstable scheme, right? So essentially, you want your scheme to be really contributing to stability for all the case. All right, this is kind of the principle of a Fourier stability analysis. There is a lot more, but like it's the idea is really already here. You can probably read a lot more about stability analysis of this kind of schemes for finite difference, finite volume, finite elements. But the idea is really encapsulated over here, right? Okay, any questions on the stability analysis part of this the class?